So, good morning, everyone. Welcome to the third problem-solving session of this course of Advanced Quantum Mechanics. Let me remind you that there was a lecture last Thursday, and we talked about creation, annihilation operators, and the promise that those are proper tools to investigate, to explore, to understand advanced quantum mechanics. It would be fair to say that from now on, we just apply these techniques to learn more and more, and also to learn how to solve some practical problems of advanced quantum mechanics. Right. Little bit organizational. If you have noticed, I put some homework, first homework package. Right, the deadline is end of this of March, and we'll also have supervised homework in the week. This session also helps you with homework, but not immediately concentrating on homework, but rather presenting how to deal with creation and annihilation operators in and different situations. So there will be 4 presentations, time allows. And yes, please, as usual, put the questions to the chat. And if the question is not answered, please speak up. Very well. With this, I would like to give the floor to Miriam.
Good morning, everyone. My contribution to this session starts with a very simple topic, and that is notation and how to simplify calculations. Yuli just said we're now moving towards practical exercises. The homework is online, so it means that we're going to learn how to apply all the theory from the lectures and from the previous problem-solving sessions to actual problems. And now notation maybe doesn't sound very fancy as a topic, and indeed it is not. I also agree with that, but it can be very useful to be smart about it, to choose notation that is convenient, that will simplify your calculations in the homework and otherwise. And so I think I have something like 3, 4, or 5 slides.
I'm sorry, I think you're muted, but I don't know if that's for me.
Sorry about that. Did you hear nothing at all, or did you just not hear the last part?
I think the last slide.
Okay, the last slide. Okay, I think I just said that I was going to open the PowerPoint presentation with a few slides on the topic of notation. So our goal is to look at notation, and the big goal on the horizon is to learn how to choose it well, and thereby to minimize risk of mistakes, of confusion, and all of this that we don't want. To begin with a few general remarks. When you encounter a homework problem or some other problem in quantum mechanics, read it carefully and then think about how you're going to write things down. What is natural for the problem? What is it asking you to do? What is convenient for the problem? Should you, for example, work in the position representation with simple wave function notation, psi of r? Or is it more convenient to work in Dirac notation? Are you interested in the eigenvalues of the Hamiltonian, for example? And imagine that these levels are labeled with n, then something like this might be more convenient. So think about what is convenient to use in each problem, because they're all different. Then the notation, kind of trivial, but still I like to mention, notation must contain labels for all degrees of freedom that matter in the problem. So for example, if there is a momentum involved, your notation for the wave function could contain or should contain an index that indicates which mode, sorry, going too fast, which mode we're talking about. So there could, for example, be psi of k. If the particle contains spin, then just having n is not sufficient. You must also include a sigma, convenient symbol, conventional symbol for spin. So you'll have Dirac notation and a ket that contains both a label for the level n and also for the spin sigma. And this is particularly important when we're going to study composite systems. And with that, I mean that there is a coherent quantum system described by a Hamiltonian, which is coupled to an environment of some sort and which can exchange energy with this environment. Then you need to tell what the state of the system is, which state it is in, and also simultaneously what state the environment is in. So you need notation for both. And then last general remark, also again maybe sounds trivial, but still it is important. Always simplify your calculations and expressions as much as possible. I'll have some examples in the slides that follow, but this is really very important, especially if, and we will have those, if there are more complex Hamiltonians that contain many indices, k, k prime, sigma, sigma prime, something else, and you're going to have double sums, complicated expressions. Always look at it and don't stop writing, don't stop your calculation until you have the simplest form you can think of for the answer or for an intermediate step. So some examples. We start very simple. Last week, we talked a little bit, last Monday in the problem solving session, about bosons and fermionic systems. Here is again, for those of you who were there, the system that we considered for bosons. Imagine that these boson, that the eigenlevels for the bosons are labeled by just index n. So the ground state is state number 1 here, and then the next first excited state is labeled by 2, and so on until level n. And you're asked to do some calculations with these bosons. For example, first to write down all possible eigenstates and then calculate the corresponding eigenvalues and so on. What notation are you going to use for this system? Now, for this system, it's a fairly simple system. There's no environment specified. It's just the bosons in these levels. So, like last week, it's convenient to use Dirac notation, and the only label you need is an index n for the level that the bosons are in. So for one particle, you can see it here, it would just be a ket with an n between the brackets. If there are more bosons, you need to specify what the state is of each of the bosons. So say there are n, capital N particles now, then your ket has to contain more numbers. You have to specify where each boson is sitting. So in this case here, we have the first 1 to I-1 bosons are all sitting in the ground state in level number 1. And then there is one boson number I, that's actually excited. It's sitting in an excited state, label 2. And then there is another more from I+1 until n, which are in the ground state. So now we have labeled all the particles and we know where each one, in which level each one is. For fermions, you can write down the same problem. So here are again the same levels. Now there is, of course, spin. So if I have one fermion, I have to specify its state, its orbital state, I should say, which is labeled by n, and also its spin state labeled by sigma. If there are two particles, you have to label each of them. You have to tell where they are. So for example, the first particle with spin up is sitting in the ground state, level number 1. Second particle, second fermion is also in level 1, but it has the opposite spin spin down, and so on for more fermions. Now, composite systems, I already mentioned them. Typically, also in the homework, you will be given a Hamiltonian or a description of a system, the following type. There will be some quantum system which evolves coherently according to the Schrödinger equation specified with a Hamiltonian. And this system will be able to exchange energy with an environment. And usually there's also a coupling between these two. So there's the quantum system, there's the environment, and there is a mechanism, a coupling between the two by which they can exchange modes, energy. So we need to label both the system and the environment. An example that we'll actually see later on in the homework. Imagine a qubit, a two-level system with a ground state G and an excited state E. And this qubit is coupled to an environment, and the environment you will also learn about is a so-called boson bath, which is described by the Hamiltonian that you can see h bar omega, and they are labeled by a mode index k. So B dagger k, bk is the B dagger is the creation operator for mode k. Boson bath. It will also come in the book and in the lectures. So there's the qubit and there's the environment. How do we write down what is a convenient notation for the states? Well, we have to label both the states of the qubit and of the environment. So for example, if you have one qubit, you could have a label G, it's in the ground state. So the state of the entire system is qubit is in the ground state. And imagine that there are no modes yet. So the environment is in the vacuum state, which I will indicate with the 0 here. Better still, especially if there are more modes involved, is that you specify which modes are empty. So add an index k to the vacuum state. There are no modes of the type k. This becomes important if you have exchange and modes are transferred from one mode, it becomes another mode, the momentum is exchanged. So then you need to specify which modes are filled and which are empty. Another way to write is with the tensor product. The qubit is in state G, and then you add the tensor product with the state of the environment, vacuum, 0 modes of the type K. If there are more qubits, we have to say which state they are in. So imagine there are 2. The first qubit is in the ground state, second qubit is in the excitant state, and let there be one mode, one K mode in the environment. So that will write down like this. And you can again also write this as a tensor product. The left part of the tensor product is the state of the 2 qubits, G and E. And the right part of the tensor is the mode in the environment, 1K. I am almost done, but just a few more words about simplification. Minimize the risk of confusion, that's how we started, and also try to minimize the risk of making mistakes. One trick that you can always watch out for is if you encounter double sums, if you have to do calculations and there is a double sum in it, if possible, regard it very critically. Look at it and see if you can't simplify it. For example, something we often see is the following. There's a double sum, K and K prime, of NK and NK prime. And this you can rewrite since the two NK and NK prime are independent, the sum over K only acts on NK, and the sum over K prime only acts on NK prime. So this is exactly the same as having the sum over K squared. And the right-hand side here is a simpler form because you only have to calculate one sum, and do not get confused by this double sum and all these indices. So it's simple things. It's not a very deep thing or so, but it can help you tremendously in the homework to simplify your notation and to evaluate as little as you can. only one sum instead of two in this case. It's not always possible, but regard your expressions critically, check if you can simplify more. If a Hamiltonian contains a sum, and this could also be a sum of operators or a product of operators, then don't become confused by this sum, which can be an enormous sum over many operators with different indices. But first of all, regard only the operators. This you will really need while doing the homework. Only look at the operators and start looking at how one term in the sum, only a single term, can be a product of operators, but only one product, how that acts on a state. So then you can forget about, for the moment, about the sum, about all the coefficients that may be in front of these operators. Only focus on the operators, take one term from the sum and let it act on the state. Usually by this stage, you already know what the eigenstates are of the system you're looking at least of the uncoupled, of the coherent system. And then you can you can look what the operators are doing on a state. And once you have an idea of that, what a single term does, it often gives you an idea of which terms in the sum are important, which will actually be non-zero, which will give you a finite answer. And after you know that, it's easier, much easier to evaluate the entire sum. It saves a lot of work. We often see students that start to evaluate the whole sum in one go. They write out this Hamiltonian, all the terms explicitly, and then they have this huge Hamiltonian acting on a state, and it's terrible to look at. That's actually really true. So don't do that. Only take one term from the sum and let it act on the state. So for example, there's a Hamiltonian like this. This is a Hamiltonian of the type I mean. The Hamiltonian is a sum, a double sum in this case. A is some coefficient, not important to specify for now. And then there are the operators. Let's say they are creation operators for a certain particle that is labeled by C operators, and it also has a momentum index. And then there is a different type of particle, which is created by B dagger, and annihilated by B. So there's a product of three operators here acting on each state. So when you are asked to evaluate this Hamiltonian, pick one term from the sum, only this one, for example, and let it act on the eigenstates and see what it does. And often you will find that you don't need all the sums in the term or all the terms in the sum because many of them will give you zero. So if H, the Hamiltonian, is acting on a state consisting of certain, let's call them modes for the moment, and there are two types, C and B, look at what a single term does, and that often gives you an idea of what the whole sum does. I think we'll come back to this point in some later stage of the course, because it's really important for the whole of the course. All right, that was all I wanted to discuss. Let me just check if there are some questions. I lost my chat. Sorry, I see that there are some questions. Let me see here. You are muted. So yeah, the muted problem has been solved. Could you go back to the second slide? Rines, it has been recorded. I think it's also because of time, it's good if we move on. If you watch the recording later and you still have a question about the second slide, what was stated for the end particles, write me an email and I will respond as fast as I can. All right, thank you very much. I'll give the floor back to Yuli.
Very good, thank you, Miriam. So now, Christa, this is your floor.
Okay, I hope everyone can see my screen. Yeah. Okay, so I'm gonna go through two exercises which are given as extra problems. The first one is going to be very short, and we're going to talk about statistics in disguise. It's problem 6 of extra problems. And at first, you're asked to consider the following exercise. You have an operator Z here, which writes as the exponential of a double sum of a combination of creation and annihilation operators with matrix elements. Let me use the color. Here, M is considered to be a Hermitian matrix, and what you're asked to evaluate is the trace of this operator and show that it's equivalent or equal to the determinant of the following expression. Now, there is a hint that's given in the text also that one should consider diagonalizing the matrix M, because M is Hermitian, it's diagonalizable, and it's diagonalizable by a unitary transformation. So I just wrote down again this operator Z. Here I note this, if there is no index on the creation or annihilation operators, I consider them as a row or a vector, a list of creation and annihilation operators. So I will just write the simple formula of diagonalizing the matrix, so choosing another representation of this matrix M. D is the diagonal matrix, and U is a unitary transformation. In this representation, let me see, yes, of the vectors.
Krista, do you hear me?
Hello?
Krista, there was kind of bad connection. Could you repeat last 2 minutes?
Oof. Okay.
Yeah, starting from stressing this formula, M equals U, D, U conjugated.
Sorry for that. Okay. Our connection was okay, but I'll still repeat it. So we have this formula for the matrix M, which we express as the diagonal matrix D times some unitary transformation. So we perform this change of representation to find other creation and annihilation operators which serve as a basis in which this matrix M will be a diagonal matrix. By expressing this, we simply write again the formula for Z. Here, Di is the eigenvalue, are the eigenvalues of the matrix D. And because this is just an eigenvalue and not a matrix anymore, we can put Di dagger after the eigenvalue, and we find the number operator. And now our next step is to consider that those operators are operators of fermions. So here C are the fermion operators. And we know that Ni take the values, every eigenstate can be only populated by 0 or 1 fermion. The trace is the sum over all possible states, so the ensemble of Ni states. We can express also the sum here in the exponential as the product over those I states. Yes, there is a question. I could go back. But what would be your question? Because there is a recording that will be uploaded on the Brightspace, so you could go back and rewatch it again. Okay, I'll go slowly then. Now here, I repeat myself, we have this sum in the exponential, which we represent as a product over the states I. And then every ni can take the values 0 or 1. So for 0, we get, if ni is equal to 0, we get 1. If ni is equal to 1, then we get just the exponential of the eigenvalue of the state. And we notice that this product is just the product of eigenvalues of this whole matrix. And because the determinant is invariant under unitary transformations, we can simply write the determinant that this product is equal to the determinant of 1 plus exponential of minus m, with m being the initial matrix, which is Hermitian. Now for the statistical, when one does statistics, this di, this eigenvalue is in principle just okay. So the last line here from here to here, it is true because we have just found that this is the product of the eigenvalues. So this is the matrix 1 plus exponential minus di, and this is the eigenvalue of the matrix, and the determinant of a diagonal matrix, right? Because this is now a diagonal matrix. If you calculate the determinant, then it will be just the product of every, of the eigenvalues on the diagonal. So it applies for a diagonal or non-diagonal matrix. Okay. And then di in this case can be for fermions, it's just the level epsilon I minus the chemical potential and this beta temperature. So we find the usual Fermi-Dirac statistics. Now for bosons, you're asked to do the same. This time, bosonic operators, we follow the same logic. We first diagonalize the matrix as done previously, and okay, I'll go back. D is just an operator which is a linear combination of C operators. To answer the question, I'll go back. So D is just, this is how we have represented D, or D dagger. So U is the unitary transformation. They commute because Di is an eigenvalue here of the matrix M. So it's just a number. Yeah, it's a diagonal matrix, and that's why. Okay. Now we do the same diagonalization of the matrix with a different unitary transformation possible, but it follows the same logic. And again, we end up with exactly the same expression, but this time we're dealing with bosons. So the possible values for ni here are also infinite. So ni, because of bosons, can take from 0 to infinity. And what we have to do is to evaluate this this sum over all possible ni's. And this is the geometric series or a geometric sum where our coefficient r is just this exponential minus di to the power ni. Right, and this exponential, in order for the geometric sum or series to converge, this coefficient must be less than 1. So this is just a mathematical formula that we use, and the sum is equal to this term. And again, we have a product of partition functions of every level. Here again, di is the eigenvalue. And just for fun, we can again write it as, let me answer just a question. The question is I and the I in Ni the same I? Yes. And yeah, again, using the same trick that this is a diagonal matrix, and this, because it's diagonal matrix, the product of the diagonal entries is equal to the determinant of this matrix. Okay, I'm gonna move to the next exercise because we have a lot more to talk about it here. So in our next exercise, we're gonna perform some algebra of operators, and a lot of it. If you have any questions, don't hesitate to ask, but do not try to write everything down because there is a lot of operations here. So we're going to talk about exponent of Boson operators. Okay, there are two questions concerning the last exercise. You can exchange the product and the sum, and the result is that we begin from a quantum interpretation from creation and annihilation operators, and we find in both cases the Fermi-Dirac partition function and the Bose-Einstein partition function. And another small result is that we find that for this independent system, the partition function of the whole system is the product of I partition functions of every level. Okay, so we're dealing with Boson operators. And this is problem 7 from the extra problems. And first you are asked to evaluate this commutator. So b to the power n and b dagger. Those are bosonic operators. So what we do is we write explicitly first what is the commutator of those two operators here on the right side. And we look at the term, sorry, here it's left hand side. Here it's left. So we look at this term. We take b to the power n minus 1 outside of this operator. We end up with b dagger. Then what we do is we use again the commutator relation. So we express this product. We exchange b and b dagger such that this is equal to 1 plus b dagger b, here written explicitly and already multiplied by b to the power n minus 1 from the left. And we write down the result. Okay. we do the same thing, but this time for, let me go with red. This time we look at this term, again, B dagger, and we again express it as B dagger B. The goal of this is to try and put B dagger as in front of B to the n. So we perform the same or we do the same commutator at every step and see what we're left with at the end. Again, so here we have done it 2 times, and by doing it 2 times, we end up with this. And what we infer is that if we do it n times, the result will be the following. Okay, so here it's 2 times only. Then we need to do it n times for this product. And by doing it n times, the final result will be this one. Okay. And we should not forget that this was just this term that we were looking at. So in order to evaluate the whole commutator, we need to subtract. It was the other term? Yes, sorry, you're right. Made the mistake initially. Yeah, it's this term, you're correct. And what we need to do is to subtract then from our final result here is to subtract this term in order to obtain the commutator below. So it's simple, let's say, algebra by keeping order and performing commutators on exchanging B and B dagger n times. And we finally end up with this result. Now in our next question, you're asked to employ this result from question A and to prove that for an arbitrary smooth function, f, which is a function of operators here, commutator with B dagger is equal to f prime, the derivative of f. So again, we define because it's sufficiently smooth, so there is we can expand f or write it as a series. Here we have coefficients a n and b to the power n, just Tyler or Maclaurin series. Then we plug in this formula for f in the commutator. We express again f as the sum of as a series, and what we end up is the commutator between Bn and B dagger. But if you remember in question A, we found that this commutator is equal to the following here. So if we replace simply the commutator in this formula, what we obtain is, yeah, exactly. We obtain this sum, right? This is the result with it. Sorry, let me do it again. So we substitute the commutator, right? This commutator here, and this will result, so this expression will appear here with the coefficient a of n. And we notice that this is just the derivative, right? If we have a polynomial, this is just the derivative of with respect to this B operator. Okay, now comes even more fun. We have the following equality between this function f. So f of b times the exponential of alpha, which is a parameter here, b dagger, is equal to the exponential of alpha b dagger f of b plus alpha. So we need to use our result from the previous question b. And what we do is we take this expression and we multiply it on the left by exponential minus alpha b dagger. So by doing so, we have this exponential on the left, and the exponential here will be just one identity. Now this, again, I made a mistake. It's not right-hand side, it's left-hand side. The left-hand side of the equation has the following structure. We have an exponential of an operator, x times y times the exponential of minus x. So this is somehow a useful lemma that you will never be asked to remember how to know by heart or to remember. Well, here you see that x is defined as minus alpha b dagger, and y in this case is f of b. So the lemma that we're going to use is this one, Baker-Gambo formula. And it states the following: if we have this expression, it is just equivalent of a very long sum of commutators between x and y. So x was this minus alpha b dagger, and y is f of b. So what we do is we simply replace our x and y values in the formula. First term is f of b. The second one, we already have a commutator between minus alpha b dagger and f of b, and so on. So the second term, we have two commutators, third term, three commutators inside each other. But we have already calculated this this commutator in question A, and we know the result of it. Okay, in question A we found that in question B, sorry, that b dagger f of b is minus the derivative of f. So in all these commutators can be replaced with derivatives of f, right? So we have the initial the y value. Here we have the derivative of f. Then we have the second derivative of f, because this commutator will give the first derivative, but then after performing this commutator, we'll have the second derivative, and so on in this whole series. And we can recognize that this is actually the Taylor series of f evaluated b plus alpha, with alpha being this parameter. So we began by evaluating this expression using the lemma that I showed you. And we end up that this is equal to the Taylor series of f of b plus alpha. And now for the last exercise, again, we have this we need to show that the exponential of the sum of b dagger and b weighted with different coefficients is equal to the following expression here. And we're going to use all the results that we found before. So here you're given a hint to consider the following operator that depends on S. So this is S. You see that if S is equal to 1, am I right? We deduce a similar expression to the operator that's shown above. So our method will be to derive a differential equation that is satisfied for any S, and then we're going to see for any if we can find this equality for a specific S. So we use the hint. We take this operator O of S, and we take the derivative with respect to S. Now, what do we have? Here it's the first, so here we take the derivative with respect to, I should have written it down. We take the derivative with respect to the first term, then the second term, right? They are both multiplied by this, right? By this expression here. And then finally, for example, you see if I take the derivative, so we have three terms, so it's a sum. Because it's a product, then if we take the derivative, it's the sum of three derivatives. For the final term, we take with respect to S, as you can see, and there is this coefficient in front. So I suggest that you do it yourself, because now it's very difficult to follow, I suppose, but just carefully take the derivative of this operator with respect to S. So first, right, first we take respect to this term, second term, and then it's three terms. So here is the first, here is the first, the second, and this is the final, the third one. And what we do afterwards is now we have operators, but we also have so we also have parameters, and they commute. So we first take the this term, the first term here, and we leave it as it is. Then for the second term, let me see. Then for the second term, we're going to commute because we're trying to, what we're trying to get is to have this expression, so exponential of S minus S alpha B dagger in front, and this expression on the back, such that we have a commutator that we know how to evaluate. So here we see this this common term is already on the back, and we need to combine the B dagger. So the B dagger here with the B dagger here, and the B from here with the B from here. Okay, so after performing some tedious calculations, you would find that yeah, you have a commutator between this b dagger and exponential minus s beta b, sorry. And then again, we use the result from our previous, the result of b, by replacing this commutator with the derivative of f. This time, the derivative of f is this exponential. So there is just a multiplication with respect to, multiplying it with respect to minus s beta. And yeah, ultimately, you should find that the derivative here, the derivative with respect to of the operator O of s with respect to s is equal to minus alpha beta s, and again the operator O of s. So that's the strategy. And then we have derived the differential equation. What we need to do next is to find this function O of s. And to do so, we just yeah, integrate both sides. And what we find is that this operator O of s, right, by integrating, we find it has this following form. It's an exponential or a Gaussian that's with respect to s squared. With respect to s, sorry. So it's a Gaussian function. And we write down again the definition of O, the operator, on one side. Here it is below. Sorry. Yeah, as Yuli said, is equal to 1. And then we notice that if s is equal to 1, we find the expression that we wanted to prove, but in a slightly different form. We need to yeah. This can be written just by multiplying on the left and on the right with different operators. So here we see that what do? We first multiply by, on the left, we multiply by the exponential of alpha b dagger. And then again, in next multiplication, we multiply by exponential of beta b, again on the left. That's why we have this on the left side of this exponential. And then again, we can use the result from question C. For those two functions, f of b and exponential of alpha b dagger. This time, this f of b is going to be again another exponential. And finally, we derive the formula. So somehow in conclusion, this exercise is tedious, but one needs to follow the steps carefully and try to derive the results at every the results that you are asked to derive, and just pay close attention to when you take derivatives or when you commute b and b daggers. Yeah, and that would be it for now. Do you have any questions? So the first question is, why can we write a sufficiently smooth function as a sum? Is this just a trick, or is this true by definition? It's true by definition, by the definition of sufficiently smooth. And is there a nice expression for BF, so annihilation operator? There must be one, yes. But I don't have it now. But it depends if there will be a nice expression, but it will be f of b dagger, not f of b. And I think it will be the same expression. I think it will be again the derivative.
That depends what you ask, Sasha. If you're asked about commutator of E of B, F of B and B, it is definitely 0, right? Because it depends on the same operator. Sasha?
Yes, sorry, could you repeat it?
You write commutator of B and F. If F is function of B, this commutator is 0. Because
Yeah, exactly. No, but
okay.
f is function of b dagger, or we just get the same expression as before.
Yeah. Well, in this case, you could just complex conjugate it. You get what you want.
Yeah, right. Okay.
All right, Krista, would you roll down?
Okay, so
Oh, that was quick. Okay, thank you, Krista. So let's have a break now. Let us see how much we can afford. I would say 7 minutes till 9:50. All right. Then we'll go on as usual. I pause the recording again. Good. So Max, the floor is yours.
Thanks, Yuli. I will try today a different scheme where I write the exercises or will do the calculation for yourself to simulate a blackboard. Please let me know afterwards how you like this format or if you like the presentation format better. So we tried today to solve the exercise 3 of of Yuli's book, or it's the same as the question 6 of your problem sheet. And what we do there is we try to find out what are the restrictions on a matrix L, which transforms our creation and annihilation operators as given in this equation 1 here. And these linear transformations of these creation annihilation operators will become very useful in a later stage, especially when working with quasi-particles, because in the end, we will transform from one particle, typically this B represent a real particle, we transform into a quasi-particle which can have a different physical meanings in the end, which helps us solve our problems. But you will find more about in the next lectures. I think it's next week where you discuss the superconductivity and the BCS model. Okay, so how do we tackle such a question? Yeah, first we just write what are the bosonic commutation relations. So let me just first write them here, which is given by the delta function. And we have the second commutation for the B operator, which is BK dagger, T dagger equal BK BT the commutator, which is equal 0. And we request from our finding that our final D operator should satisfy the same commutation relation. Therefore, we have dm dn dagger equal delta mn, and we also request dm dagger dn dagger equal dm dn equals 0. Now we have a set of equations 1, 2, 3, 4. And so how do we tackle this? So what we do is we use for the question A, we insert 1 into first taking the 3, where we take the commutation relationship, which gives us the delta function. And first we have to calculate actually what is the n dagger, and we get this by taking one complex conjugate 1. So this is given by sum over T L N T BT. We have to dagger this, and we find that this is correct. This is expression, and now we insert these into our delta function, and therefore we have dm dn dagger, which is a delta function mn. Now we insert these definitions for dm and dn, and this is L and K. EK. And the second sum, T, BT dagger, and here we have L. Tn complex conjugate. Now what we do is we pull out the sum. So we have here the double sum. Now we have only MK, BK, BT dagger, LTN complex conjugate. And since the operators since L is only a number, but it commutes with our operator, we can also pull it out of our commutator. And we finally have KT, L, and K, BK, BT dagger, LTN complex conjugate. And this, this we know is delta KT. Therefore, one of these sums can be eliminated, and we only have the sum over K, L, M, K, L, K complex conjugate, N. And this is nothing else than the matrix multiplication of L with the complex conjugate and transposed matrix. And this needs to be the delta function, Mn. Therefore, when we therefore, this term here needs to be the identity matrix. And in other words, L needs to be unitary. So now we have the first part of the exercise I already solved. And let's check if the other equation, especially this one or this one, gives us a separate solution. And we can immediately see that when we plug this in, when we have dm dagger, dn dagger, which needs to be 0, we plug in the sums. Dm dk dagger t sorry, did this in the correct order, which needs to be 0. And here we can again pull the same trick. We pull out the double sum and the L. I will do this now in one step. You can see it in the top one, how it works. And we have here bk dagger, bt dagger, and equals 0. But now this is also equals 0. So we just have 0 equals 0, and we don't get any further constraint. Okay, this is already the A. Now I directly jump to the B. In the B, we have a bit of a more general linear transformation, which now mixes our dm, where we now have a mixture between our annihilation and also our creation operators. And yeah, we proceed exactly as follows. We start writing up the commutation relation, and then we just plug in our new definitions of dm and dn dagger into these commutation relations and try to work out what are the restrictions. Now let me also write the complex conjugate. What I will do in the follower to save time and space, I will drop the sums and I use the Einstein notation where I sum over indices which are neighboring here. I will not write them on the top due to stylistic. So for the dn dagger, we have now the following. connection where we just need to transpose this equation here on top, and we get this equation here, and we again plug them into our commutation relationship for the dm and dn, or where we get the data function. So we first use dm dn dagger equals data function mn. We plug 1 and 2 in. And we get, write it here. And what we now have to do is we have to multiply these out, and we get 4 terms, LMK, BK, sorry, there's a mistake in this equation. Here, there's no dagger. And we get also the second terms, the second row. And again, since these L and M operators commute with our creation and annihilation P operators, we can pull them out. I will do that once here as the extra step, but in the following, I will just always skip this. EK, ET dagger. And now we can plug in our commutation relation. So this is 0, this is 0, this gives us the delta kt function. And this gives us negative delta kt function. And we are left with LMK, LKN dagger minus MMK, MKN complex conjugate. Sarah, yeah, exactly. In equation 2, I corrected this one. And we know this needs to be the delta function. Therefore, we have now a different condition, which is given by this equation. Now, if we use a matrix language, this means that we have LL dagger minus M dagger equal the identity matrix. But now we have to check also if the second commutation relation gives us a different one. And I will go slowly, I will go shortly over it. So we have now the dm dn equals 0. We plug in again all the terms. Dagger and we multiply out. That's a good question. Yes, there are, but these are not discussed in this exercise here. Or the question was if there are transformations which transform bosonic to fermionic. Here you go. And the last one, which is oops, sorry. And we have again, these are 0. And these are 0. And in the other twos, we get the delta function. We here get the minus delta k t. And here we get the plus delta kt. And what we get is LMK MNK minus MK LNK. Now, this equation here, we can rewrite this by because this needs to be 0. We have now LMK MNK equal to K. Now rewrite always the second one. And transpose it. Therefore, we can identify this for the matrix. Terms. And this is the solution for the second problem. I will now skip the C due to timing. I will just quickly go into it very quickly to see what are the difference? First, we have, instead of commutation relation, we have anti-commutation rules. And the big crucial step is for A, we get the same condition, but for B, we get a different condition because the anti-commutation rules are, you don't get the minus sign if they're in the different order. And what you get is instead the plus sign. Therefore, you get the equation for fermionic. And you get this also relation also for the fermionic case. With this, I would give the word to Julie. If there are any more questions.
Right. Thank you, Max. We are a bit out of time, so let me switch to my presentation. And let us see. What I'm going to talk about is the greatest puzzle of this course. And usually these puzzles are for students, but that particular one is rather a puzzle for us instructors. Right? Let me explain. I shall reveal you that all homework problems, almost all exam problems follow the same structure, which is given by Petubation Theory. What does it mean? It means that we have some simple Hamiltonian. Let's call it H naught. That Hamiltonian has some ground state. And this situation is perturbed by a Hamiltonian. Let me call it HP. P stands for perturbation. This Hamiltonian is some Hamiltonian made from creation-annihilation operators of the products and sum, and this is a sum over elements. And the question, which is usually second or first question for this exercise, is to, for student, is to give what states are obtained from J by a line. I will stress it twice. Elements of HP. This is a very crucial question, which enables us to deal with perturbation theory. This question is crucial, but the answer on this question is simple and doesn't have to do complex calculations whatsoever. The biggest puzzle is, of course, that a certain part of students, say 1/4, do not answer this question. With catastrophic consequences for the whole examination or homework, because this question is crucial indeed. Again, answering to your questions, Rinus, We are talking about simple Hamiltonian, which has some ground state. And elements of HP work on this ground state. And the answer to the question which I formulated, what are possible states which can be obtained from ground state to from that. Sorry for my writing. Good. Let me give an example. I could give more because actually all homework, all exams are based on this. So we have electrons and photons. I believe it's homework of the second package, but I'd better talk about this now. So there is simple Hamiltonian, which is a sum over electron energies. Let me call A electron operator. And sum over photon. So did I say photons? I mean phonons. Phonon energies. All right. This is simple Hamiltonian. One can just replace these values of A, dagger A, B, dagger A by occupation numbers. Ground state, we sketch electronic spectrum and all states below some energy and within some interval of K will be occupied. So the ground state is, and all energies of bosons are positive. So the ground state is 0 for all bosons, vacuum. And for fermions, we have some set of occupation numbers, a set, remember, where nk is 1 if modulus k is smaller than Fermi wave vector. All right, so it lies in this window. All right, so that's simple. And then perturbation comes. Perturbation, let me first say in words, what does it do? A perturbation is a term in the Hamiltonian which describes emission of a boson with changing electron state. So let me write it as follows. I want to annihilate electron in certain state with wave vector k. I want to create a boson with wave vector q. Then owing to momentum conservation, the created electron has a momentum k minus q. Right. All these terms, they come with different coefficients, coupling constants. This is just a number. It depends on k and q. All k and q can be vectors. I just spare time not writing arrows. Good. Any Hamiltonian has to be conjugated. So I add complex conjugation to it. Let's see, what have I forgotten? I've forgotten the sum. So basically the summation over two vectors, K and Q. Fine. All right, so how to answer the question, this crucial question? Do not look at whole Hamiltonian. This is mistake. Some people just apply the whole Hamiltonian to the state. There's a computation which takes an hour or so. And after this computation, they don't answer the question. There was a question which I want to assess. Let's see. Oh, that was, thank you. Don't mention. Right. So what I want to do, I just take a single element of this HP. What is the element? When I talk about element, I can skip the coefficient. I just concentrate on this expression. So what does it do? This needs to annihilate an electron. It means that K must be smaller than Kf. Otherwise, there is no electron to annihilate. A photon can be created, all right? And an electron has to be created in this state. That also implies that K minus Q must be bigger than Kf. There must be empty space for this state. So, as a matter of fact, we have a state which can be parameterized with two K vectors. For instance, K and Q. All right. And this is nothing but, let me switch back to this color. Hey, Dega. Working on the ground state. So this is the answer which we require. You see, it's quite simple. No complex calculations are required. You can write it in many forms. You can use these rows of occupation numbers, but that's also not necessary. I guess it's most compact notation. But if you give like in terms of occupation numbers, there's no mistake. Right. So this was my presentation. I hope that I will thereby solve the greatest puzzle of your course, that all of you will answer this question correctly. Francesca asks, does the Hermitian conjugate part of the perturbed Hamiltonian does not play a role? In this particular case, it does not. Let me explain why. If I conjugate it, so what do I do when I conjugate? I have to put operators in opposite order and conjugate them. So that's what I get. This will be conjugation of this term. So what you see here is an annihilation of a phonon. But if it works on phonon vacuum, it gives precisely, right? Let me repeat that if I ask a question about this course, usually the answer is 0. There are very many zeros in advanced quantum mechanics, and we will have to make a good use of them. This is an example of this use. Since there was annihilation operator, you don't have to think about this. You can only create phonons in the circumstances. If they were excited photons in an initial state by some means, it would be a different story. But for this particular case, you can only annihilate the photons. So again, this question has a simple answer. Perhaps that would be most instructive statement about this. Don't go complex, just think how things work. This annihilation creation operators, they have very clear operational meaning. You don't have to write formulas. You just imagine that particles are killed, erased, created. So that's it. Any questions about this? Again, for us, it's a very important part, and I hope that you will make no mistake from your homework and in your examples. They are just momentum in the momentum representation. I'm not sure what does it mean. What it was implied in this Hamiltonian is a momentum conservation. So the sum of all, perhaps I have to show it again. There is the sum of all momenta of annihilated particles and the sum of all momenta of created particles must be the same. Very good. I see no questions, so let's see. It was an answer to my question, but then why do they show up in the operator? Let us see. Let me look at this expression again. How momentum is related to creation and annihilation. Momentum here labels different single particle states, levels, where different fermions and bosons can be created and annihilated. Instead of momentum, I could write some other letters, and if I consider not a system of plane waves, but some other basis in single particle state. Then there would be no momentum conservation, and these three operators would have all different indices. Does this answer your question, Sarah? Yes, indeed. Indeed, Q is related to boson momentum and K to Fermion momentum. We have two independent momenta in the problem. You could kind of take any names. You could write Q for bosons and K for bosons and Q for fermions. What is important, there are two independent momenta for each state you can create, right? That's why I can label the state just, to shorten notations as K and Q. That's one possible labeling. I could, for instance, do the following. I can label it with two wave vectors of electrons, and I would write it as a Dega K prime, A, okay, B, and that will come with, let's see, K minus Q. I'm sorry for writing about this. And what else? AK, all working on the ground state. Good. So this is just a matter of labeling. What is important that there's a plenty of the states. There's a set of these states which can be labeled with two wave vectors. Fine. If there are no other questions, let me thank you for your attention. Let me stop